That's where we ended. Yeah. So we talked through all those solvent terminologies. So practice a little bit. So as soon as I start recording, I'm going to pause the recording. Okay? Classify each of those 4 compounds according to the definitions that we defined on Tuesday. So the terminology we talked about is listed up at the top. We could start with the polar versus nonpolar, which is ultimately referencing the types of bonds present, be it polar covalent bonds or nonpolar covalent bonds. Right? What we recognize is that we could differentiate our polar covalent bonds into 2 different force classes, dipole-dipole and hydrogen bonding, which necessitated now the definition of protic. So our 3 different classifications are ultimately protic, polar aprotic, and nonpolar as our solvent classifications. And what those are tying back to is the intermolecular forces. What intermolecular force do we expect from nonpolar?
London dispersion.
Pen work. Why is it? Yeah, there it goes. Our London dispersion force. Our polar aprotic gets us what force?
Dipole-dipole.
Dipole-dipole. And our protic gets us
Hydrogen bonding.
hydrogen bonding. Once we've identified both the classes and their responsible intermolecular forces, we can now look at the structures and say what bonds do we see present within those structures. For that first compound, what bond do we see that stands out?
Yeah, C to the O.
The C to the O. That C to O bond is a
Dipole-dipole.
polar covalent bond, which leads to a dipole-dipole force, which is a solvent classification, would then be our polar aprotic. I believe what I said on Tuesday is that I would be okay with just calling that polar, with the aprotic being implied. Okay. When we move to the next one, we're looking at our structure and saying what bonds do we see present? We see that O to H, which is our polar covalent bond. A polar covalent bond leads to a dipole-dipole force. Now that we have that dipole-dipole force, we can also look for the presence of a hydrogen bonded to oxygen, nitrogen, fluorine within that polar covalent bond, which then means we have hydrogen bonding. Once we've identified we have hydrogen bonding, we can then call it protic. Kind of makes sense? Shorthanding it, the next one is going to come out as protic, and then the last one will come out as nonpolar. Make sense? Questions about any of that? All right. So there's lots of kind of secondary steps along the way that we're responsible for being able to quickly navigate so that we can get to the final answer for our definitions. Okay. That takes practice to build that up. Okay. So now we've got an extra fun one. What we're now going to talk about is solubility and look at examples for our solubilities. So don't treat this necessarily as a quiz, but what you're trying to do is as quickly as possible find a match between the solids and the liquids to decide which ones would mix. Okay? So to start off with, we could look at our solid number 1. Okay? What bonds do I see within that? I see carbon to carbon and carbon to hydrogen. Both of those are nonpolar covalent bonds. Because they're nonpolar, they're going to give me LDF forces. Okay? Now what I'd want to do is go through and look at my solvents and find something that would also match LDF forces. Because solubility is like dissolves like. Like forces dissolve like forces. Okay? Because again, we don't see forces. What we see are our bonds. What we're looking for is a thing that has nonpolar bonds. The thing that has nonpolar bonds exclusively is going to be our best bet. Our nonpolar bonds, carbon to carbon and carbon to hydrogen, the best bet for this one would match out with D. So as a pairing, I would put 1 and D together. That's how I would format it. I'd say, hey, our pair is 1D, because 1 should mix with D. With that, take a swing at the rest. And it's a bit obnoxious because it makes it look like it's all simple and real easy. It's not necessarily that simple and easy. Okay, go through, see what you see, try and make those pairings and we'll talk about some things as they pop up, is that we look at that first example we did and we go, oh, it's a perfect clear like match. They're both nonpolar, it's fine, that's how it works. Okay? Most systems fall in some middle area, which means more than one thing could match. So what we should be trying to go through and do is see what we see within each of those. So hopefully for structure 2, what we're seeing is that O to H bond, which is our hydrogen bonding, or which would lead to hydrogen bonding, I should say more appropriately, which means the solvent we want to find is one that would allow us to hydrogen bond. Okay? Well, how would it allow us to hydrogen bond? For this to form a hydrogen bond to something else, what has to be out here? What does that red question mark need to be? O, N, or F. Does A give you O?
Yes.
Does B give you O?
No. Well,
Yes.
yes.
Does C give you an O, N, or F?
Yes.
Does D? No. So based off of 2, what we might be able to do with that analysis is say it is not D. Okay? And we could very well go through and say A, B, and C are all valid. Okay? Which is okay. Okay? What I'm trying to get you to do is look for those patterns behind it. Between A, B, and C, is there a difference in what forces they're projecting? Man. Yeah. So when we look at A, all we see is that polar covalent bond between the carbon and the oxygen, which is going to lead us to dipole-dipole and dipole-dipole only. If we look at B, we have the C to O, which is that polar covalent, which is our dipole-dipole, but we also have that O to H. That O to H is going to take us to the next level. That one can hydrogen bond. C is also going to generate that hydrogen bond. So what would that suggest? That if I'm going to try and dissolve 2 with hydrogen bonding already embedded in it, that maybe B and C are better options than A. Does that make sense?
Mm-hmm.
So we could potentially go through and say, well, not A as much, but B and C seem reasonable. Okay. What about 3? We have that polar covalent bond, which takes us to a dipole-dipole force. So now what we want to do is find the solvent that generates just that dipole-dipole force. We could again say no to D. Do we get dipole-dipoles in C?
Yeah.
Do we get dipole-dipoles in B?
Yeah.
Do we get dipole-dipoles in A?
Yeah.
What does that suggest? A, B, and C are all possible answers again. Okay. Of those, does any closer match? A is probably the closer match, so we might go through and say A is our preference, and we would ignore B and C. Could B and C still dissolve? Yeah. Okay. But again, what we're looking at is those possibilities, and then once we've got possibilities, ranking which one we think is closest. Okay. It's that thought process that I want to see behind that. Make sense? Which then takes us to 4, and 4 is the most challenging one. Most people go through and see all of that and say, oh, it's nonpolar covalent, it's therefore going to be D because it's nonpolar covalent. But we do have that positive charge there. And that positive charge is a cation. As soon as we've got an ion, we should be looking at ionic forces. Do we have a solvent that is ionic? No. Why not?
You didn't draw one.
Because Mike didn't draw one. Why did I not draw one? Ionic compounds have very strong intermolecular forces, which means when we look at an ionic compound, generally speaking, they're solids, not liquids. That's why it's not drawn. Okay? Because for the phase predictions, we wouldn't predict it to be a liquid phase. Okay? That's why it's not shown up there. So at this point, we are going to try and dissolve ionic compounds into our solvents, and since we can't use ionic liquids because they aren't easily accessible, we're going to have to pick the best choice out of that. Since we don't have an ionic-ionic match, we need the next closest match. What's the next closest match? Hydrogen bonding. So we'd now move through our systems and say which of these generate hydrogen bonding. We'd again say B and C. Okay? Is there a difference between B and C?
Yeah.
How so?
C has the double bond.
Not only does C have the hydrogen bonding that we get in B, but C also has a dipole-dipole force, which is also a very polar force. Right? Whereas in B, it's London dispersion as our kind of secondary force. What would that suggest? C probably has slightly stronger intermolecular forces, and there's probably a slightly larger chance that I'm going to be able to dissolve compound 4 in solvent C than in any of the other options. Kind of make sense? What I really want you to do is not just say there's one match. What I want you to do is to recognize there's multiple matches, okay? Of those multiple matches, which one is the best one? And theoretically, it's which one is the best one to test first before I move on to the next solvent, before I move on to the next solvent to see which one actually worked. Because that's what we would do in the lab. I need this compound to dissolve. I've got this solvent. They might work. Let's test it. Okay? But we don't want to be testing solvents like D for compounds 2, 3, 4 because compound D doesn't align at all with their intermolecular forces. That's kind of the pattern recognition. We good? Okay. Which then means, well, look at this. Solvent application. Okay? So what we're about to move into is starting to look at our reactions, our chemical reactions. Okay? Once we've got chemical reactions kind of described, we will also add another layer to it, and what we'll look at is mechanisms. How does a chemical reaction happen? And what we're looking at in these two scenarios, officially the bottom one's not formally drawn out, is looking at the same chemical reaction. If we look at our reactants to the far left, we have this R carbon chain with chloride and the iodine connected to it. The product is the R carbon chain with chlorine, R carbon chain with chlorine. So what overall happened within this reaction?
Chlorine and iodine switch.
We have a switch of the chlorine for the iodine. What we've done is a substitution. We've substituted one atom for another. Okay? So this is now sort of moving into our next system because what we're saying is we have substitution as a reaction type. That's not how you spell substitution. Abbreviate. Okay? The next part, once you've identified the type of reaction, you will also drill into how that reaction happens. Okay? So there's the what of the reaction, what is it, and then there's the how it happens. The how is a mechanism. Okay? The bottom reaction is actually drawn a little bit to give us some mechanism information. Okay? How is the bottom reaction as drawn different from the top reaction? There's a curved arrow in it. When have we seen curved arrows before? With resonance. So those curved arrows that we use in resonance are explaining how electrons move. Okay? How it changes the bonding patterns within an individual molecule. Okay? Well, what's the point of a mechanism? To show how we change the bonding pattern between molecules. Well, it's all about how the electrons move. So guess what we use? The exact same system as we used for resonance, we now use for mechanism. And we talk about how the electrons move. The difference for a mechanism is I'm now making and breaking sigma bonds. That's the chemical reaction. Resonance, we could only really make and break pi bonds because the overall atom connectivity stayed the same. As soon as we move to an actual mechanism system, now we're talking about making and breaking sigma bonds, which means other bonds can quote unquote move. They aren't really moving, we're just changing where the electrons are located. So if we look at this single arrow, what are we saying has happened? The arrow's starting at that sigma bond. and it ends at the atom. What does that mean? Well, that means I've taken the electrons in the bond and I said you exist only on the iodine. What happens? Well, the iodine, instead of having 3 lone pairs, now has 4 lone pairs. Okay, so we should see that in our drawing. Okay, and we've already addressed that we aren't very good about that, right? That our heteroatoms, we almost always not draw our lone pairs. When it gets to mechanisms, I'll try and be better about it for the sake of our class so we can understand that. Okay? But not only did it gain those electrons, if it gains those electrons, it becomes negatively charged. So I have to specify that charge now. But if it gained electrons, what happened to the carbon?
Lost
It lost electrons, and it is therefore positively charged. So what we have is just, here's our starting point, just some structures, and then we add instructions on top of those starting points. Those instructions are our curved arrows, saying this is where I want you to move those pieces. Okay? Then we draw the result of those after our reaction arrow. And then if we need to, we have to draw more, because if we look at the next step, we didn't finish. Okay? We have charged species, and in particular this carbon is particularly reactive. Why is that carbon particularly reactive, but the iodine less so? That's a rule you actually know, believe it or not.
It wants to complete its octet.
There's the statement. The carbon is missing its octet. The iodine is satisfied. So that carbon is now very reactive and can react with something. Well, what does it need to react with? If it's positively charged, what should it react with? Something that's negative. So we can reach out into solution and say, where's there a negative? We could have the iodine share back. That's talking about the reverse reaction, which everybody's going to hate. Remember you talked about equilibrium reactions in chem230? No? Serious? Okay. You should have talked about equilibrium reactions because it's in the competencies, at least within Maricopa. I don't know about Yavapai. Okay. You should have talked about equilibrium reactions. It usually happens really fast, and you... Yeah. Well, you remember me probably talking about them. Do you actually remember anything about them?
I remember you talking about them.
Yeah, that's usually how it goes. It's the end of the semester, and it gets crammed in at the end, and nobody remembers it. Okay? So our equilibrium reactions ultimately say that we can reverse reactions. So what we could do is we could add another curved arrow here and say those iodine electrons come back with that positive. What would the result be? We would go backwards in our mechanism. Right? Do we want to go backwards?
Not really.
No. Okay, so let's see. Is there another thing that we could do?
War.
The chlorine could react. So I could have the positive go to the chlorine. You said no. Isn't that what's happening? I have the positive and the chlorine. Don't they hook up? Why are you saying no to me?
In the drawing, you're supposed to move the electrons.
What does our curved arrow show the motion of? Electrons. What is this curved arrow showing the motion of?
Literally not.
The atom.
No.
We don't show motion of atoms when we look at mechanisms. We only show the motion of electrons. What does that mean about this arrow? It's wrong. It should be flipped. The arrow should start at my negative and it should end at my positive. What happens? That lone pair has now become a bond connecting the carbon to the chlorine. Okay? The chlorine now only has 3 lone pairs because the other one is shown as a bond. The chlorine was negative. It's now lost a pair of electrons due to that curved arrow, which means it's now neutral. The positive has gained electrons, so it is now neutral. And we have our final product. Up here, we have the same product. Yeah? Okay. If we were to add curved arrows to the top, what do you think we should do?
Do 2 arrows on the left.
If we look at that top mechanism, okay, because our mechanism says how do we get from reactant to product for each of those reaction arrows. Reactant to product, reactant to product. Up here, it's saying all of that stuff has to happen in one step because I only have one reaction arrow. So what does that mean happens up at the top? The chlorine has to share electrons with that carbon so that it can make the bond in my product, and at the exact same instant, the iodine has to take the electrons away from the carbon so that I get the lone pair on the iodine. So this top one requires 2 arrows in one step. The bottom one broke those arrows into different mechanistic steps. Kind of, sort of? Okay. So these are now our mechanisms, okay, which is a bit of a leap, particularly because when we look at the top of the slide, it says nothing about mechanisms, it says nothing about reactions, it says solvent. Okay? Why do we care about the solvent? Well, we care about the solvent depending on how the reaction functions. Okay? And this bottom reaction, what stands out is I form a carbocation. We said that's insanely reactive. If it's insanely reactive, does it come into existence?
What do you mean come into existence?
For it to come into existence, the iodine must leave the structure. It must take the electrons away. If this is very reactive, can the iodine leave?
Not without being replaced by something?
No. And if it can't leave, then this doesn't work. We would need something to help this come into existence if this mechanism, this explanation of how, was to actually come into fruition. Could we add something to our reaction to help stabilize this? Yeah. What else could we add to our reaction? A solvent. So the choice of solvent could change how the reaction happens. Okay? If I want this thing to come into existence, what I might do is choose a solvent that would stabilize that positive. Okay? Well, what solvent would stabilize that positive? Something that's negative, but that would suggest what force? Ionic, and as Ty suggested, our ionic compounds are solids, not liquids. That doesn't work. So if we can't use an ionic forced solvent, what should we move to? Hydrogen bonding. And it turns out for this bottom reaction, the solvent that we choose to use is a protic solvent. Because the most important thing for this reaction is that thing to come into existence. And if I use a protic solvent, that protic solvent has that large difference in electronegativity between the hydrogen and our oxygen, nitrogen, or fluorine. That oxygen, nitrogen, or fluorine is very, very, very negative. What can that negative do? It can sit near that positive, allowing it to exist for a little bit. Once it exists for long enough, now the chloride could come in and react. So depending on our mechanism, the solvent choice becomes really important. Well, what about in the top one? What needs to happen in the top one? Well, it's all happening at once. We don't have to do anything. Does the chloride have to exist? Yeah. What happens if I use a protic solvent?
But it wants to repel.
What does the protic solvent bring in? A hydrogen bonded to an oxygen, nitrogen, or fluorine, and then something out here, which means we have a large partial positive and a large partial negative. What does that large partial positive do to this negative?
Wants to go towards it.
It goes towards it, which means how strong is that negative?
Well, after it goes towards it, probably not as strong.
It's not as strong. If the positive weakens our negative, can the negative attack? It slows it down. So a protic solvent is a horrible choice. I don't want a protic solvent because I need that species to be negative to attack. Didn't we need the negative over here? We did once this came into existence. I had to get this first before I worried about the negative. So because the mechanism changed, my interpretation of what becomes important or valuable will also change. Make sense? Okay. Is that challenging? Yes. Yes. No mistakes. I completely agree with you. That is flippin' difficult. Okay? But that's what we're trying to do when we look at OChem, is we say, what are all of these pieces? What are our structures? Now, what are the things that would allow me to get those structures to talk to other structures? That's intermolecular forces. How can I ensure that those structures start to transfer electrons? That's now looking at our reactions. That's looking at our mechanisms. Now, how do all of those things come together to either help that or hurt that process along? It's nuts. But that's what we do when we study OChem, is we look at each of those stages. That's also why we reduced the periodic table to just 10 elements and not 118. Because 118 would make it more miserable, I guess. Better description. Kind of, sort of? Okay. That's a pretty deep application, so that would be a more challenging topic to kind of address when we talk about solvents and intermolecular forces. Again, low frequency on an exam. Other things that we should address when we talk about solubility. So let's take a look at some examples here. If we've got water, because we're now looking at named things, we should probably actually look at structures, because that's how our structures interact. So we've got water, right? And if we're drawing it appropriately, we've got the bent structure for our water, and we want to mix it with ethanol and decide, does it mix? So if we look at ethanol, what do we see?
That they both have hydrogen.
They both have hydrogen bonding, so do they mix? Yep, and sure enough, they do. Okay, now let's take a look at acetone. Should it mix with water? No, why not?
It only has the
Dipole-dipole versus hydrogen bonding, so we'd say no. Guess what?
it could.
It does mix. They mix pretty much perfectly. Same as with ethanol. Okay, well, why? Well, the polarity of that oxygen-carbon bond was enough that it could interact appropriately there. Okay, so dipole-dipole molecules can dissolve in hydrogen bonding. Okay, carbon to chlorine. Is that a polar covalent bond?
Yes.
Yes. Okay, so I put in another one. Should be pretty polar, right? Should that mix with water? You're like, last time I guessed, you said I was wrong. That's the point, whole point of this slide, for the record.
I'll say no.
Okay, and it turns out, no, it doesn't dissolve. Chloroform does not mix well with water. It has that dipole-dipole, that polarity, but that dipole-dipole is not strong enough to interact with water. Okay, and we're going to look at two more, one of which isn't on the list. Okay, we'll look at diethyl ether. So diethyl ether, carbon, whoops, that was an oxygen. Those are all hydrogens. So diethyl. So we're looking at the black parts are two carbons, so those are ethyl. There's two ethyls, so it's diethyl, and then it's an ether saying we have the oxygen in between them. It's our nomenclature system. What do you think? Should it mix with water?
Yes.
Yes? Why?
Because maybe it's the dipole force is enough.
Okay, so we're saying the oxygen-carbon bond is a dipole force, okay? Just like with our acetone and all of that, shouldn't it mix? Turns out, no, it actually doesn't mix. It mixes horribly. We actually take advantage of that and use diethyl ether instead of dichloromethane as a solvent for our extraction technique. We should have used diethyl ether. Okay, so it doesn't mix, which says that that dipole force, maybe for it to be a dipole force with oxygen, it has to be a double bond. It can't be two single bonds, because the two single bonds don't make it polar enough. Right? THF. Tetrahydrofuran. Does that dissolve in water?
No.
No, why?
Because dipole, with two sigma bonds.
Dipole, 2 sigma, that matches exactly what we had for the diethyl ether. In fact, it's the same number of carbons. Tetrahydrofuran perfectly mixes with water. What the hell? All of this goes sideways. Okay, and what I'm trying to point out is not because I want you to memorize that. What I want you to do is exactly what Devin's doing. I think it's this because of this. Perfect. I don't care if you're right. What I care about is, are you using a logic flow that makes sense behind that? What I want you to recognize that it is vastly more complicated than that. And we end up having to increasingly add rules behind it. Remember, like forces dissolve like forces is not a rule, it's a guess. And it's a guess that works, maybe 60, 70% of the time. Right? But there's that 30 to 40% of the time that's floating out there that it doesn't work perfectly, and there's other things that factor in. Okay? Why would THF mix but not diethyl ether? What do you guys think? Clean up the diethyl ether and make it look a little bit nicer.
Shape.
You're telling me the shape. Isn't that the flippin' same shape? You just didn't draw one extra line. You might be able to push on shape a little bit. Why does the cyclo matter?
I thought you said something about the size impacting it in some way, but I can't remember.
The size can impact it, but here I think you're on thin ice to call this a size difference.
So what about branch? Carbon's branch.
What kind of bonds are in this?
Not polar. Well,
We have
not
polar,
that one.
covalent, and non-polar. Yeah. Keep going. What other kind of bonds are in here? What other ways can you describe these bonds? What were you going to say? No? Okay. We've described bonds a bunch of different ways. You want me to give you another way to describe these bonds?
Yes.
Single bonds.
Oh.
You're going to say what? Okay, sigma. That's the word I wanted to hear. Okay, so they're sigma. What is special about sigma bonds?
You can rotate.
They can rotate. When we look at this, what are those bonds?
Sigma.
Sigma bonds. Can those rotate?
But not much.
Why no? Did you say no?
Actually, yes, and I said no.
Oh, well, that's not fun. They can't rotate. Why can't they rotate?
They're more locked into the cyclic structure.
The cyclic structure locks them in place. They can't rotate. Why is that important? When I look at this drawing of my diethyl ether, this hydrogen can come and interact with that oxygen. And then what could this sigma bond do? Rotate, causing this massive nonpolar tail to do what? Whap! Knock the hydrogen away, effectively a baseball bat. I'm not talking about a sigma bond rotation for this to come up and swap the water away. What do I have to talk about? The entire flippin' molecule to flip over to rotate. Fast motions due to the sigma bond rotation, slow motions due to molecular vibrations. That changes how the molecules interact with each other. That's why we see differences in solubility. So we get our first baseline with intermolecular forces. I just don't want you to run through life saying, oh, it's always intermolecular forces. They're really important, but there's a lot of other factors that can contribute that kind of take some of that away. Okay? And there's cases where you'd be like, well, shouldn't this one be insoluble because it can flip or it can't flip? Okay? And we find the opposite thing happens because there's something else. There's another little piece that's contributing to the puzzle behind how that thing is explained and how it works and functions. Kind of, sort of? Okay. So, I think we're now done with solubility. What can be done with our interactions with our solubility? We can talk about salt and water and oil, but the big deal that I would really kind of push to is soap. How does soap help stuff dissolve? It emulsifies. How is it emulsifying? What is it doing? Yeah, I just know the words. That's cool. That's not a big deal. Chemistry is supposed to be addressing kind of what the meaning of those words are. What's happening with soap is that soap has a hydrophilic, so hydrogen bonding part of the molecule, and a hydrophobic part of the molecule. And so what happens with soap is that when we rub it on our hands and smear it around, the hydrophilic part, the hydrogen bonding part, interacts with water. All the dirt and grease on our hands interact with the other part of the soap molecule. And effectively what we create are micelles, where all the dirt is trapped on the inside. Now what do? We put our hands under the water. The water sees all the hydrophilic part, the hydrogen bonding part, and washes it all off our hands. Cool. Well, why is that big of a deal? What happens if we scale that up? What if we now have 2 layers? We have a hydrophilic part on the inside and a hydrophilic part on the outside. We can do that by aligning 2 soap molecules tail to tail. And we'll go, why would you ever do that? Well, scale that up even larger, and what do you have?
It acts like a cell membrane.
You have a cell membrane. Okay? So these intermolecular forces are things that are used to create barriers for our individual cells so that they aren't exposed to the outside environment. And it's all based off of the intermolecular forces. Okay? That's kind of neat. It creates an impassable membrane, but what's the problem with it if it's impassable?
Then things can't get in and out.
Things can't get in. Well, I don't want germs inside, but I might want energy. I might want food. So we have to build systems that allow the penetration of that membrane. Okay? And those systems are now selective for certain things. How are they selective? Intermolecular forces. Those intermolecular forces will reach out and partner with the different parts of the molecule and connect to bring them in. This is why some viruses or bacteria are good at infecting things, because what do they mimic? Good stuff. So the cell membrane grabs a hold of, oh yeah, this is great, this is food. Whoop, nope, it wasn't. This is actually a toxin. Okay? And it's all back to those intermolecular forces and how they key and kind of lock together. So it is kind of a neat process, and you can push it a lot, and there's lots of studying in it, and yada, yada, yada. Okay? But what we'll go ahead and move on to is now pushing a little bit into our structure. Okay? So if we looked at these compounds, we could draw out structures. Right? We've got HCl. That's a Cl. We have OH. We have H. I'm going to say CH3 out there. Okay? And what I'm trying to call attention in this case is those blue bonds. Okay? Are those blue bonds different? Yes. What kind of bond do we have down here? Non-polar covalent. Polar covalent. Polar covalent as well. Okay? Does the reactivity change for those? Yeah, it changes significantly. Methane. What does methane do? Fat load of nothing. It just sits there as a gas. Okay, it only does anything interesting when you throw a match and some oxygen at it. Okay, so we have to run a chemical reaction with it. Water. Water is a liquid. That was a gas. Changing the intermolecular forces changed that. Okay, we go up here to HCl. Did the chemistry change even further? Yeah. Ooh, the chemistry changed a lot there, right? It's not just HCl versus HO. HCl is an acid. We now change it even more significantly. Well, why does it all of a sudden change? It's still a polar covalent bond. Well, what's the difference now between our oxygen and our chlorine? Good. What did you just do?
Looked at the periodic
Yeah,
table.
we looked at the periodic table. And we look for our oxygen and our chlorine on the periodic table, and we're now trying to look for those differences that might call attention to what's happening there. That's awesome. They're in different rows. Well, what's different about the rows? Say it again. True, maybe. Oxygen versus sulfur are in different rows, yet they have the same number of valence electrons.
Electron
Electron
activity.
activity does change across the row.
Size.
Size ultimately is the biggest change here. We're getting a very large difference in size. That size differential is contributing to the reactivity difference between these, which means we now need to start thinking about when we're connecting these atoms, how does that change their ultimate reactivity? HCl we call hydrochloric acid. Cool. Okay? So what we're saying, as an acid, it does what? What is the definition of an acid?
Donates protons.
Donates protons. So if we're looking at HCl, we get H plus and Cl minus. If we said water acted as an acid, it would give us H plus and OH minus. Does water act as an acid very much? No. How do we represent that in our reaction? Everybody's favorite, equilibrium. Does it produce very much H plus and OH minus? No, it produces a tiny little amount. And the tiny little amount that does form rapidly does what? Reverts back to H2O. So we could see that in our reactions. What does that mean for us? Well, that means something about the reactivity of our species. So we could now start to compare these two and say what made them different. Why is this one willing to produce tons of this, but this one is not? Okay? And guess what we're going to zero in on? We're going to zero in on the oxygen versus the chlorine. Why do we not look at the H plus?
Because it's the same.
It's the same in both. Why do we not look at the H2O or the HOH in our HCl? Why would I choose to look at Cl minus and OH minus instead of those? What does resonance show the motion of?
Electron.
What did our curved arrows show the motion of?
Electrons.
What do we see when we look at our Cl minus and our OH minus? Electrons. So if we can understand something about how those electrons are stabilized or destabilized, that could allow us to predict something about a reaction. Are those electrons as obvious in the starting structures? Nope, because they're drawn neutral. So we look at the charged result and say, how does that affect? Okay? So we could now start to look for those differences, and we would do exactly as Jasmine suggested. We could look at the difference between oxygen and chlorine. We look at the periodic table, and we say there's a difference in electronegativity, and there's a difference in size. Which one is more important? Why is the size more important?
It changes.
If it's more electronegative, what does it do with the electrons?
It holds
It holds
them closer.
them. So if I'm comparing these two reactions and I say oxygen is more electronegative, what does that mean about the stability of the negative on oxygen versus chlorine?
It should be more stable.
It should be more stable. And if it's more stable, what should this reaction arrow do? Produce product. It doesn't. Which means our interpretation of electronegativity, it's not that it's flawed, it's that there's something else factoring in. What's that something else factoring in? Well, what's our difference between oxygen and chlorine? The size. Chlorine is larger than oxygen. Why does that matter? What we're talking about is the electrons and how stable they are, how happy they are on an atom. The more electronegative an atom is, the more it's collecting and holding those electrons. Okay, that would explain stability. Why would size matter?
Because of the number of protons that affect the electrons.
So we could try and look something at that. This is the example I like to use for size. Here's chlorine. Here's our oxygen, yeah? We're talking about a single electron making it negative or positive, or negative or neutral. So there's our single electron in both of those. And what we want to discover is how happy that electron is. We've got a couple analogies that we can work with. The first analogy, imagine that is you. Are you happy in a space where you've got lots of room or where you have no room? Lots of room, okay. That makes it more stable. Okay. Next thing, if we talk about reactivity, it's how that electron reaches out and touches something else. You get to be the something else. You get to reach out and stick your hand into one of these circles. If you touch the electron, we're going to electrocute you. Which circle do you stick your hand in?
The bigger one.
You stick the bigger one because there's less odds of interacting. You just described why it's less reactive. The chloride is less reactive. It is more stable. That size in this comparison allowed us to see that was more relevant than electronegativity. So we can now start to think about the things that contribute to stability and overlay them on top of our reactivity. The reactivity we start with is acid-base. Why do we start with acid-base? Guess what all of your Gen Chem was about? Acid-base reactions. Whether you really fully processed that or not, you think about everything you did, it was the transfer of a hydrogen from one atom to another. That's all you studied. Okay? They tried to make it fancier, but ultimately that's all it was. Okay? So that chemistry is so well studied that theoretically we can start there and say, remember all of the stuff that you learned, let's apply that acid-base stuff and let's start working through that. Now let's make it more difficult and say it's not hydrogen anymore, it's something else. What changes about the picture? Well, the fun thing what changes about it? Really nothing. You'll end up using the exact same rule sets to explain the reactivity. And that's beautiful. Right? So if we're now talking about kind of our reactivity, we're moving into our simple chemistry, our acids and bases. This is all you really studied. Okay? There were 3 definitions that you theoretically encountered. Okay? I would argue all of Gen Chem really only talked about the Arrhenius definition. Okay? You talk to most general chemists, they'll say, no, we talk about Bronsted-Lowry. I would have said that too when I taught Gen Chem. But it's really all you're talking about is the Arrhenius definition. I don't want to talk about the Arrhenius definition because ultimately it is so outdated it is not useful. So we aren't even going to worry about it. Theoretically, you all studied the Bronsted-Lowry acid-base definition. So, what is our Bronsted-Lowry acid? Cool. I'll change that wording a little bit. You said proton donor. We're not talking about nuclear changes. We're not adding protons into a nucleus. We're talking about the proton being a hydrogen ion, so it's H+. So it is okay to call it a proton, and I'll call it a proton as well, but we're talking about H+, not nuclear protons. Okay? So an acid is a proton donor. What is a base? Becomes our proton acceptor. This definition improved on the Arrhenius definition because it keeps something in common. So when we're talking about our acids and bases, what it's keeping in common is the presence of H+. So our Bronsted-Lowry is strictly how do we transfer hydrogen ions. That's it. Okay? And it turns out that that definition is a bit narrow, and we can broaden it a little bit. So if we look at our proton acceptor, let's just say H+. What does our proton donor is H+, donated H+. It has to donate H+ to something. What does that something need to supply? And if we think back to our Bronsted-Lowry bases, what is the classic base you interact with? Sodium hydroxide. That's OH-. And when we're looking at putting that together, that's how we get H2O. This is why we study acids and bases according to the Arrhenius definition. Arrhenius is referencing hydroxide. It's the formation of water because everything we do in Gen Chem is in water. The Bronsted-Lowry definition tweaks it a little bit and says the H plus is coming from an acid. The thing that accepts said H plus is now the base. That allows this thing to be lots of different stuff. Arrhenius leaves it as pretty much hydroxide. But I could switch it to NH3. And if I draw out a Lewis structure for NH3, it's going to have a lone pair of electrons. Why is that important?
It makes it negative.
It's not negative. What is the base doing in this reaction? Yes, it's accepting the H+, but how? That how is a pretty critical word that we've addressed a little bit earlier in today's lecture. When we're talking about hows, we're talking about what? Mechanisms, which is the transfer of electrons. If we're going to talk about the how, what is the base doing? We're taking an arrow starting at our hydroxide and aiming it at the H+. That arrow is showing how that lone pair of electrons on the oxygen is being shared with the hydrogen. What could the NH3 do? Share a pair of electrons. What if I drew CH4? Could CH4 act as a base? No, because it has no electrons to share. So when we're looking for our base, it's not so much that it's accepting H+. It's thinking about now what it's doing. The base is sharing electrons. It's a very subtle flip in the definition or thinking about this process. Okay? But Bronsted-Lowry starts at the acid and says, well, the acid's the most important thing. How does it function? The Lewis definition goes through and says, well, chemistry isn't happening by moving atoms. Chemistry is happening by moving electrons. So what are the electrons doing in this process? So we start pretty much at the base and say our base is an electron donor. And our acid is now the electron acceptor. This could become confusing really quickly because I could say, define the acid. What am I talking about? Is that a Lewis acid or is that a Bronsted-Lowry acid? How do I know? Okay. And if we push it even further, the Lewis acid-base definition is so flippin' broad that guess what it applies to? Everything. Okay? The Lewis acid-base definition is like saying, we're all people, so we should all get along. That's not how it works, buddy. Okay? Bronsted-Lowry narrows that so that now we can use those acid-base definitions to define particular chemical reactions. The Lewis definition is way too broad to manipulate. Okay? So what we'll end up doing is when we say acid-base, we are explicitly, in this class, talking about Bronsted-Lowry. And if we want to talk about the transfer of electrons that don't involve hydrogen, we need a new word choice. That new word choice comes in as nucleophiles and electrophiles. And we'll pick up there on Tuesday, right? Because we're done at 1:15, aren't we?